to functions. Functions is kind of a big topic in year 11. There's like a lot of content, I guess. And it's super important to get a good grasp on this now because you do so much with functions in year 12. And a lot of it you don't go over again in year 12, but you're just sort of expected to like have remembered it and to remember how to do it. So super important for you guys to get a good grasp on it now. So our functions essentially are just equations or graphs where there's only one y value for every x value. So there are lots of types of functions, such as these ones. Some of them have discontinuities, which means they're not just one straight line. So if you look at this graph of the reciprocal, there is a discontinuity. You probably can't see it because this is fairly zoomed out, but if you zoomed in enough, you would see that there is nothing that actually hits the y-axis. So if we look at this graph here, the linear graph, you can see each of these x values only has one y value. Okay, same thing with this quadratic. Each x value only has one y value. Now, some people start to get a little bit confused when you're looking at quadratics. It is okay if one y value fits more than one x value, as long as each x value only has one y. Okay, so if you look at this here, 1 and -1 both hit the same y value, but 1 only has one y value and -1 only has one y value. So that's why this is still a function. Okay. Same thing with the absolute value. You'll see that there's, two x values that hit each y value. That's completely fine as long as each x value only has one y value. Doesn't matter how many x values each y has. Okay, so that's a little bit confusing to think about, but bear with me. Same thing, square root function, each x value's only got one y. Our cubic, each x value's only got one y value. And same thing that we've discussed about our graph of the reciprocal as well. So yeah, with these functions, we can test for how things, or whether a graph is a function. And the way we do that is through the vertical line test. So this is the test you use anytime you want to test whether a graph is or is not a function. When you draw a straight line down a graph at any point, so at any and every single point on this graph, that graph will only intersect your straight line once. Okay, so essentially what that's saying is that if we've drawn our vertical line through x equals 1 here, if it only hits the graph once, then there can only be one y value. And no matter where we draw that straight line along this graph, it will only ever intersect it once. So we can say, yep, this graph is a function. You guys might not have seen this yet, but this is what your graphs of your sine, your trigonometric function sine looks like. So spoiler alert, that's a function. And then you've got graphs of your circles, which you can see at any point. If you drew that straight line at any point on this graph, it would hit it twice. Okay, because each x value has two y values. And so then we can say for this one, it's not a function. Okay, so just let you look at that for a second. Okay, so probably the most important thing to take away from functions in year 11 is looking at the domain and range and working out how to calculate, I guess calculate's not the right word, but figure out your domain and range. So super duper important. So when we're looking at the domain is the x values for which a function is defined. So essentially, where on the x-axis will our graph exist? Then we've got the range, which is the y values for which a function is defined. So essentially, where on the y-axis is our function going to exist? Okay, so for example, if we're looking at find the domain and range of y equals x squared, you'll look at your parabola. We've graphed it here for you, and you'll see that this graph slowly trends outwards. So if we've put no limit on that, it can hit any x value, right? Because it'll just keep getting wider and wider and wider and wider. The higher it goes up the y-axis. So we can say for this that the graph can take any real value for x. And so then you can write that as the domain equals all real x. Okay, because at any x point, we can generate a y value. There's not a single value, a real value for x that you can sub into this equation that wouldn't give you a y value. Okay, then when we've got range, we can see, when we're just looking at this graph, that our graph is going upwards only. Okay, it's not going down, and we can see that it starts at y equals 0. So we can say that our graph is going up and up and up and up and up, and there's nothing that's going to stop it going up. But we're not going to have any value below 0 for y. So then we can say that our range is y is greater than or equal to 0. Okay, so that's that for domain and range. Super important that you understand how to work this out. Super easiest probably way to do it is to graph and to actually look at the graph, and then from there it's super easy to look at, okay, where does it exist for x, where does it exist for y? Okay, so also important to understand even functions and odd functions, which we'll look at in a second. But our even functions are functions that are symmetrical about the y-axis. Okay, so essentially that's saying like the left and the right are the exact same of the, thinking of like left of the y-axis and on the right of the y-axis. So their line of symmetry or reflection, depending on how you want to think about it, is about the y-axis. Okay, so for example, you can see this in a semicircle. It's the exact same on the left and the right. And then you can see it in the parabolas as well. The exact same on the left and the right. Now, a question type that you guys might get given is to prove that a function is even. If you ever get asked to do that, the only way to prove a function is even is to show that f of x is equal to f of negative x. So essentially what that's saying is if we put negative x into our function, so let's look at this one for the parabola here, we would get the exact same value as if we put in just x. Okay, so if we're thinking about this, when y is equal to x squared, we get, y is equal to x squared. But if we put in negative x and we got y is equal to negative x in brackets squared, negative x squared and x squared are equal to the exact same thing because that squared will cancel out our negatives. So for both f of x and f of negative x, we're going to get y is equal to x squared. Okay, and that's how we can prove that our functions are even. Okay, and then the converse of that is looking at odd functions. So our odd functions are functions that have symmetry about the origin. So it's like if we spun this around the origin, we could eventually get back to this exact same graph if we just spin this up and round, so that this point now hits up here. So when the graph is rotated 180 degrees about the origin, you'll get the original graph again. So this is seen in cubics and in hyperbolas. So you've got your hyperbola here and your cubic here. If you guys haven't seen these graphs before, that's what they are. And just like when we had the even function, we can also use a little formula to prove that we've got an odd function. So the way that we do that is by showing that f of x is equal to negative f of negative x. Okay, so if we've got fx equals x cubed, then it's an odd function if negative x cubed gives us the same thing as f of x, which for the cubic it does. Okay, so that negative f just means the whole thing, our whole function is negative, and then the negative x says that the x within our function is also going to be negative. And if you can prove that f of x is equal to negative f of negative x, then you've got yourself an odd function. And the only way to prove that a function is odd is to prove this. Okay. So another super important thing that you guys want to be able to make sure you can do, at least by the end of year 11, is to solve a quadratic. So there are 3 methods that you guys can use to solve your quadratics. You've got factorization, which is when you make your function equal to 0, you find the factors that go into it, and then you solve each bracket for equaling 0, and you get there. You can complete the square, which I'll be super honest with you guys, in the HSC you probably wouldn't be looking at doing, just because it does tend to take up a lot more time, and a lot more like working and thought, like just a lot more brain power than doing factorization or completing the square. But if it works for you, it works for you, and you can do it. I mean, it does get tricky with some questions, and yeah, things just get a little bit harder when you're doing this, but essentially just making both sides be able to get square rooted, and then you just solve from there. And then you've also got your quadratic equation, which I'm pretty sure is on your formula sheet, so don't even worry about remembering it. Your quadratic equation is super good, and when I was doing my exams, it was always my go-to, unless the question said to factorize or complete the square, just because it's a little bit foolproof. When you're looking at factorization and completing the square, there's a lot of, I guess, like guessing and checking that goes into that to making sure that these things sort of work. Whereas this is like a formula that you can honestly just put in your calculator and it'll give you your answers. With this, I guess what a lot of people forget is that you do have to check for plus and minus, which you can't put plus and minus into your calculator at the same time. So you do have to remember to check them to get both answers. But yeah, I would honestly say quickest way to do it is your quadratic equation, then followed by factorization, and then completing the square. So yeah, that's how you solve your quadratics. And essentially when you're solving your quadratics, you're solving for the x-intercepts. A lot of the time, when you get given these in your exam, you are just solving it to solve them. But the application of solving your quadratic is to solve for the x-intercepts of a parabola. Okay, so I'm just going to leave this there for like 20 seconds, just so you guys can look through each of the different methods of doing it. Okay, so then we've got the discriminant is the last sort of bit of functions that we're going to be looking at today. So when you're looking at your quadratic formula, you've got ax squared plus bx plus c equals 0. When you solve this using the quadratic equation, the part you put inside the square root is called the discriminant. Okay, and your discriminant is symbolized by this little triangle, which is the Greek symbol for delta, as part of the Greek alphabet. So essentially, your discriminant or delta is equal to b squared minus 4 times a times c, which again is just what exists underneath the square root sign of your quadratic equation. So the discriminant will tell you if the roots of the quadratic equation exist, and it'll tell you about the nature of the x-intercepts. Now, the reason that this occurs is because if whatever this is equal to, if it's less than 0, you're going to get a negative number, and you can't have a negative number underneath the square root sign. So essentially that's saying that there are no x-intercepts, like there's no points where x will your graph will intercept the x-axis. So essentially no x-intercepts. If it's greater than 0, then you will get x-intercepts. And then if it's equal to 0, you'll get x-intercepts as well. But we'll look at what the difference is between those two in a second. So for when your delta or your discriminant is equal to 0, there is only one solution to your graph. So there's only one x-intercept because both of your roots are going to be equal. Now, when you think of this, it's because when we're looking at our quadratic equation, we've got negative b squared plus or minus the square root of b squared minus 4 times a times c. Sorry, it's not negative b squared at the beginning, just negative b. So essentially, if we've got 0, it's going to make no difference whether we're plussing or minusing it, because plus 0 minus 0, same thing. So we're only going to get one solution to our graph. That solution is going to be real and rational. And so as a result, you'll see that your parabola will only touch the x-axis in one place. Okay, so that's what it looks like if you've got discriminant that is equal to 0. So then the difference is when you've got discriminant or delta that's greater than 0, you're going to have two solutions for your quadratic equation. So again, if you're thinking of this in terms of your quadratic formula, you're going to have plus and minus, and it's going to make a difference whether you plus or you minus whatever your discriminant is. And that's how you end up with two solutions. Your solutions will be real, and they may be rational or irrational. So you may end up with, like lovely x-intercepts of like 1 and minus 1, but you could also end up with like, the square root of 3 and the square root of like 2. So they could be rational or irrational. Your parabola is going to touch the x-axis twice because you're going to have two solutions, which means two x-intercepts. Because like we were saying before, when you are solving using the quadratic formula, you're solving for x-intercepts. And then this is what you call an indefinite function, because the value of x could be positive or could be negative. You could have two positive x-intercepts, you could have two negative x-intercepts, one negative, one positive. Just means if your discriminant is greater than 0, that you're going to have two solutions. And then finally, if 0 is greater than delta or greater than your discriminant, you're going to have no solutions to your quadratic equation. These are what you call non-real roots. So there's no solution to the quadratic equation, and you can't have the square root of a negative number. You can't, in real terms, you can't have the square root of a negative number. So when you're looking at this, you're going to have no x-intercepts, because no solutions means no x-intercepts. Okay, so graphs that look something like this, or, maybe they'll sit like here and just never touch the x-axis. You never really know. So, that's how you use your discriminant. Important to know how to use, important to know what it means. The discriminant comes up a lot in application of other questions. Just super important to know what it means to have a discriminant that's equal to 0, a discriminant greater than 0, and a discriminant less than 0. And then to also understand, by looking at a graph, what the discriminant will equal. Okay, so looking at a graph, if you only see it touch the x-axis once, you can immediately know, okay, the discriminant is going to be 0. if you're looking at a graph and there's two x-intercepts, immediately you can recognize, okay, the discriminant's going to be greater than 0. And then if you're looking at a graph and there's a discriminant less than 0, immediately you can recognize, okay, the discriminant is less than 0. Sorry, I worded that the wrong way around. But yeah, that's essentially the key points of functions that we're going to look at today. So